In this section of chapter 5, I would like to discuss about energy. Energy tells us about the ability to do work or transfer heat. So one can use energy in order to move an object. If you push an object and if there is a displacement, that means you used your energy in doing work. Energy can also be used to cause temperature of an object to rise, and we're going to show you an example in a minute. Here you can see energy is used to move an object over some distance. That's what the player is doing. So work is defined as force times displacement. You apply the force, and because of that force there is a displacement happening, and product of these two would tell us how much work was done. In this case, you are seeing how heat energy is being used to raise the temperature from one object to the other. In this particular case, you see water on the top and there's a flame underneath. The flame is due to a reaction between, say if it's due to natural gas, the natural gas, when it burns in oxygen, it gives off heat. So that heat energy is being transferred to this container of water. So the water temperature goes up. So in other words, heat energy can be used from warmer objects to cooler objects. Kinetic energy is due to motion of an object, and this is defined as half times mass times velocity squared. So if you know the mass, if you know the velocity, you can calculate kinetic energy. Now potential energy is due to location of an object. In case of a chemical reaction, is due to chemical composition. And we are going to explain that later on, that how these potential energy changes from one chemical composition to another composition, which leads to exothermic or endothermic reaction. That means in some cases energy is given off, some cases energy is absorbed. Electrostatic potential energy, you probably read this in physics, which is given by Q1 times Q2 divided by D. So this is the charges. So Q1 is one charge at two so this is the distance, and Q2 is the second charge. So this is plus, this is also plus. They repel each other in this case. So they repel each other, and it will be given by product of those two charges divided by the distance. And also there is a constant K. Now we are going to define what is called system and surroundings. System is that part where you are focusing your attention. Say you are looking at this container where you have gas molecules. So I'm focusing only in that container, and that's why that's the system. And everything else outside would be surroundings. Conversion of energy. Energy can be converted from one form to another. For example, this person at the top of the hill has a high potential energy, and there is no kinetic energy at this point. But when she comes down, potential energy is converted into kinetic energy. And what is going to happen is the velocity is going to increase as she comes down, because potential energy would be converted into kinetic energy, and at the very bottom there'd be no more potential energy, there'd be all kinetic energy. So from this example we know that one can convert energy from one form to another. The first law of thermodynamics. The first law of thermodynamics tells us that energy is neither created nor destroyed. In other words, total energy of the universe is constant. If a system loses energy, it is gained by surroundings. Now we are also going to define what is called internal energy. Internal energy is the sum of all kinetic and potential energies of all components of the system. Often we use the term E to represent internal energy. Internal energy change is defined as final internal energy minus the initial internal energy. Now, this can be greater than zero or positive, or it could be less than zero. Now, let's assume that you had $7 in the pocket in the morning. In the evening, say you have $27 in the pocket. So how did it happen? Your mother is quite generous and she gave you $20. And so your gain is $20. Similar thing can happen in a chemical reaction. Energy or heat exchange can happen, or as reactants change to products, this kind of changes can happen. If initially reaction has smaller amount of energy and finally reaction have a larger amount of energy, that excess energy has to be absorbed. So absorption of energy or heat is called endothermic process. Opposite can also happen. Again, at the beginning, say before you went to the mall, you had $30. And you went to a candy store. When you came back home, you have now $10. What happened to the difference? Since you went to the candy store and you gave it to the person who works over there and you bought candies. So you spent basically $20 or gave away. Gave away in the sense that you bought candies. That's why there was a money transfer. Same thing happens in a chemical reaction. If initial energy is greater than final energy, that excess energy has to be given off. And this is the process. When energy is given off or energy or heat is given off, is called exothermic process. When it is given off to the surroundings, if you have water in the surroundings, the water gets heated up and temperature of water would go up. In case of endothermic process, heat would be absorbed from surroundings if water makes the surroundings and the temperature would go down. Change in internal energy, delta E, is given by two quantities. Q is the heat being added to the system from surroundings, plus W, which is the work done on the system. So both these quantities need to be added because work done on the system, that generates heat. So that's why the heat that is gained from surroundings plus the heat that's gained because of the work done on the system need to be added together to get total change of internal energy, or WE. The sign conventions are shown on the top. When Q is positive, that means heat is gained by the system. When W is positive, that means work is done on the system. Minus means work is done by the system. Now let's try homework problem number 527. So let's work on 527, page 198. It says that calculate delta E and determine whether the process is endothermic or exothermic for the following cases. A, Q value is given 0.763. Q equals to 0.763 kilojoule, and W is minus 840, and W is minus 840 joule. and you need to calculate delta E and also write down whether it's exothermic or endothermic. Now Q is positive, or positive means energy is absorbed, and that's endothermic process. So that's endothermic. Now let's calculate delta E, which is given by Q plus W. In this case, Q is 0.763, and change the W in kilojoule. So it's minus. So don't forget, we're doing this, Q plus W. Now in this case, W itself is minus, it's negative, that's why we need to use the negative number. Minus 840 divided by 1000, that's 0.840 kilojoule. And when you subtract this, that is going to give you the final answer. So minus 0.763 minus 0.840, and they're all in kilojoule. And make sure you check these, check all these numbers so that I haven't used any wrong number. This gives 0.077 kilojoule. And this is endothermic reaction because in this case Q is positive or heat is gained. Similarly, you can do part B. In part B, they're saying that system releases 66.1 kilojoule of heat. We're kind of running out of space here, so let's write down these quantities on the top. B, Q is minus 66.1 kilojoule, because they're telling you that energy was released. So this has to be exothermic. So this is exothermic. So you determine exothermic or endothermic just by looking at Q value and its sign. So in part B, they're saying that system releases 66.1 kilojoule of heat to the surroundings, while the surroundings do 44.0 kilojoule of work. So W is positive, 44.0 kilojoule. So basically you add these two quantities to get delta E value or change in internal energy. Let's do now part C. In part C, they're saying the system absorbs 7.25 kilojoule. So let's write down Q is 7.25 kilojoule. That's plus because it's saying that system absorbs 7.25 kilojoule heat from the surroundings while the volume remains constant. When there is no change in volume, there will be no work done. Work is defined by force times displacement. If there is no displacement, then there is no work done. So in this case, delta E, which is given by Q plus W, which would be, since W is 0, this would be simply 7.25 kilojoule. And since heat is positive, so this is an endothermic reaction. In this slide, we're showing you that internal energy is a state function. It doesn't depend upon how you reach a particular state of matter, and it only depends upon the state of the matter itself. Let me explain that to you with this example. Say you have 50 grams of water at 100 degrees centigrade. So that's the boiling temperature. You cool it down to 25 degrees centigrade. Now still I have 50 grams of water now at 25 degrees centigrade. So here. I can also get water at 25 degrees centigrade starting at ice temperature of 0 degrees centigrade. So 50 grams of ice at 0 degrees centigrade. I need to heat it and finally I can reach 25 degrees centigrade. So when I reach 25 degrees centigrade, internal energy is going to be the same. So it doesn't matter how you reach the internal energy, from ice or by heating up ice or by cooling down boiling water. So that's why internal energy is known to be state functions. As I discussed in last slide, that internal energy is a state function. So it doesn't depend upon how you arrive at that particular state. So same can be said about change in internal energy. It depends only on initial and final values, not how you arrive at those states. So keep that in mind. Both internal energy as well as change in internal energy are state functions. That means it depends upon initial and final states, not how you reach those states of matter. I just mentioned that internal energy E or change in internal energy delta E are state functions which depends upon only the initial and final states. However, that's not the case in case of heat or the work W. They are not state functions. So we are going to explain that to you by giving you two examples shown on the left hand side of this figure. On the left hand side you see a battery, and the energy of the battery is being used up by heating. So the battery is going to be completely discharged by conversion of its energy into heat. So how much work is done on the left hand side? Nothing, no work, only heat. So battery gets discharged because of its energy was completely converted into heat. And so the change of state was from here to here. Now think about the right hand side situation where battery is being used for running a fan. As fan moves, work is done. So battery not only works in turning the fan on or running the fan, it also produces some heat. So in second process, even though we're going from same two states like charged battery to discharged battery, however, this time you see some heat generated and some work done. On the other hand, in first case, there is no work done, all heat. So you can see, depending upon how you run the process, you may have different amount of heat and work. So this suggests that Q or heat and work or W are not state functions. They are path functions. They depend upon the path, how you're doing the process.